All right. Hello, everyone. Welcome to the IACS Distinguished Lecture Series. It is my great pleasure to introduce our speaker, Professor Anima Anandkumar. Anima is a Bren Professor at Caltech and Director of Machine Learning Research at NVIDIA. She was previously a Principal Scientist at Amazon Web Services. Anima has made many important contributions to machine learning and also in her earlier part of career to signal processing as well. For her research, she has received several honors, such as the Sloan Fellowship, Career Award, Young Investigator Awards from the DoD, and faculty fellowships from Microsoft, Google, Facebook, and Adobe. Her research focus is on unsupervised artificial intelligence, optimization, and tensor methods. Today, she will talk about very exciting recent advances that build new foundations of zero-shot generalization with applications in using artificial intelligence to accelerate scientific discoveries and engineering progresses. Anima, you have the floor. Welcome.
Thank you. Now it's great to be here virtually. Hope everyone's doing well and gearing up for the holidays. So yeah, let me start sharing my screen. Give me 1 second here. I hope you all can see the screen. So, broadly, I want to talk about how AI has so much potential for handling challenges in the sciences, right? And, you mentioned like about zero-shot generalization, right? Because in most cases, we want to be using the trained model on scenarios that are very different from the training data. And that's what makes this much more non-trivial than a straightforward application of a supervised learning method. And so before I get into how we are doing it, let's see what we are able to accomplish. One of the recent results that we showcased at the GTC conference, and Jensen Huang, our CEO at NVIDIA, showed in his keynote, was the ability for AI to solve a lot of challenging scientific simulation problems. And one of them is in the realm of weather prediction, right? So indeed, you may have come across many recent works that use machine learning to do weather prediction. But what is still an unsolved problem is to do it at extremely fine spatial resolution, right? So ideally, you want it all the way down to 1 kilometer. For a lot of, say, looking at climate risks and extreme weather risks. But AI models in general are not able to do at such a fine resolution. And so what a recent method has shown is making strides in being able to really improve the resolution of spatial modeling and go all the way down to 25 kilometers now. And doing that while being 100,000 times faster than the numerical methods. And we also see many other applications such as carbon dioxide sequestration. If you want to look into solutions for reducing emissions, right? The many scientists hypothesize that at some point we would need to capture carbon dioxide and store underground in addition to other ways of carbon capture. And so modeling the complex phenomena of how carbon dioxide would interact with water and be having a pressure buildup amongst the rocks is really important. And so here again, we've seen benefits of using machine learning and being 60,000 times faster than the current numerical computations. And so just to kind of show you some videos on both these applications, here you see that these contours, the purple contours, are the high wind speeds predicted by our model. And what we see here is this 2016 Hurricane Matthew being predicted quite accurately, you see the actual trajectory in red, and our model in purple is able to predict how that would evolve over time, and compare that to the white lines, which indicate the current NOAA predictions, right? That's the National Weather Service. And what we see is that these machine learning models are not only more accurate in this scenario here, but also 100,000 times faster than numerical calculations. So you're getting both the benefits of speed and accuracy. And same with like the carbon dioxide sequestration. As I mentioned, the idea is to model the pressure buildup deep underground, and we are able to do that over a span of 30 years and be faster than traditional methods, while also being more accurate than standard machine learning models such as convolutional neural networks. So that's the aspect of looking at can we build new methods and new foundations for these kind of highly multi-scale simulations, right, and natural phenomena, and how do we then, right, employ it in these number of applications. So that's one set of results. In another set, we've been looking into the realm of drug discovery, right? So the ability to search over this enormous space of molecules, right? So we barely scratched the surface in terms of which molecules could be useful as drugs. And what's limiting is the ability to accurately predict the properties of these molecules. And ultimately, if you do it all the way at the quantum level, then you know everything about the molecule, right? So the Schrodinger's equation is the fundamental equation that governs all molecules, all matter around us. But back of the envelope calculation shows that if you try to do that exactly brute force, you would need more than the age of the universe on the current supercomputers just to calculate it for a molecule with 100 atoms. So what this says is, yes, we in this case know what we want to calculate. If we could calculate that exactly, we would be able to precisely pinpoint the properties of the molecule. But this is just so out of reach. The questions are, can we then come up with approximate methods? So it turns out that even the numerical methods that approximate this Schrodinger's equation, such as DFT or density functional theory, are still extremely slow. And so what our machine learning methods are able to show are the ability to speed up by 1,000 times compared to the DFT calculations, and while being as accurate and be useful directly in downstream tasks, such as predicting properties and using it in workflows in a number of applications. So one standard application is looking at geometry optimization, right? So can you kind of look at energy minimization under this model and predict its structure? And this is where our method, ARBNet, is faster and more accurate than the traditional methods. And more recently, in an exciting work that got a lot of attention was, in fact, recently in New York Times, both online and in print, the ability to do a billion atom simulation of the COVID-19 or the source, the SARS-CoV-2 virus, and understand how it interacts in the aerosol and in the mucin, right? So how this is able to propagate in the aerosol and get into our system and interact with the mucin. And so one aspect of that work has been to look at predicting the binding energies much more accurately by using these quantum mechanical calculations. And this, we are able to do it for the first time on thousands of atoms. So this would be impossible with traditional methods. And so that's what has been exciting to see, the development of the methods and then put that in the pipeline with other methods, right? Both AI and numerical methods together. I think that's where we will see a lot of really good benefits. In some cases, machine learning may completely replace the traditional methods. In others, we can augment it in creative ways, get speed ups, be able to do entirely new large-scale simulations that wasn't possible with traditional methods. And, before I get into the details of how we are able to do that, I'm going to give you some overview of other algorithmic developments that I feel are important, right, in order to not just use it in scientific applications, but also many others. And especially in this realm, the trustworthy AI is the ability to, right, have beneficial uses to humanity in a broad sense. But the aspect that I want to highlight here is the uncertainty calibration, right? So if you talk to scientists, the first one, one of the important things in so many applications is, can it give the right uncertainty, right? Because in so many settings, you don't know the ground truth, right? So you want the right uncertainty that goes with the model. But we do know standard deep learning tends to be overconfident, even when it's wrong, right? So we've seen stark scenarios of this with, say, the gender shade study, where on darker skin tones, right, there is not just mistakes, but there are high confident mistakes, right? And that's hugely problematic. So, like this aspect of trustworthy AI would also be important for scientific applications. And so one case of this is the ability to understand safety, right? So in this example here, you saw the drone in one case land smoothly, in another case have this aggressive landing. And, at some point, the drone would just break down, right? So we should think about, for safety, the right uncertainty calibration, because if your uncertainty is wrong, you cannot be safe in autonomous applications. And, and we have come up with methods that look into doing uncertainty estimation through the lens of adversarial risk minimization. This is a classical statistical method, but we've now made this practical and scaled this up for, not only these kind of control applications, but also vision applications with distributional shifts. So I won't get into the details here, but I'm emphasizing that this is also an important facet. Another important aspect is the ability to do federated learning, especially on healthcare data, right? Or other scenarios where there are privacy concerns. And this is where the NVIDIA Clara platform is built with these requirements. And in the beginning of the pandemic, 20 hospitals within 20 days built an AI model by looking at data distributed across different hospitals and without having to worry about disclosing the sensitive patient data. So again, right, so I would say the field is still in its infancy in coming up with differential privacy or other kind of guarantees, but doing it at the full scale of current models. But we are seeing interesting developments there. So far I talked about machine learning to speed up scientific simulations. There's also the other side of the coin where we can use simulations, right, to train AI models. And especially in robotics, this is a huge aspect because you cannot get enough real world data if you want to do, say, reinforcement learning at scale or any kind of, adaptive learning. And that's where, we've looked at many applications that have GPU accelerated simulations. And so we can do reinforcement learning on thousands of scenarios and agents, right? This would be impossible in the real world. And by doing hierarchical methods, right, that do not overfit to simulations, we can again transfer that to the real world. this is also the aspect of zero-shot generalization, right, or few-shot generalization. We cannot afford to do a lot of real-world experiments. So how do we go from what is trained in simulations to the real world? And this is also a lot of new algorithmic developments we've done in this process. And same is the case with another application where, the online adaptivity, right? So you've trained your model now, right? The environment is changing or certain assumptions you made are changing. How do you adapt? And this is also where, we see like our method called Oscar compared to the classical operational space controller is able to do decent, zero-shot generalization. But if you ask harder tasks, for instance, right now in training, it's just drawing circles, right? So if you ask it to draw a square, it does a better job than the classical methods. But if you ask it to write down the robot, right, it requires online learning, right? It just zero-shot is not enough. You need to then adapt. And it's able to do that because we have come up with methods that incorporate inductive bias, right? That incorporate essentially the Newton's laws of physics, but on top of it also have the adaptivity. So you're baking in the physics, but not limiting to a model assumption and allowing it to adapt. And this combination is also important for especially tasks that require online adaptation. So another facet is the availability of supervision, right? So, here I've shown this on the standard videos, but especially, if you think about healthcare applications, right, the same things apply, right? It's very expensive to go and label everything. And so can we reduce the labeling costs? And so what you see here is the use of just bounding box supervision, right? So you only have these bounding boxes for training, but you automatically get instance segmentation and correspondences through self-supervised learning. I mean, it appears magical, right? So you only have this information during training, but you can get very precise masks and correspondences. But that's where is the power of self-supervised learning, the ability to, right, like as you can see in this video here, get really precise instance segmentation masks. And I think there's a lot of promise there. And same like kind of right with the neural network architectures such as transformers. How do we design the right version of it to have inbuilt robustness? And so what you see in this example here is, even though it was never trained on this noise, it's able to handle that pretty well, right? Whereas earlier convolutional models were not able to do that. So I think there's a lot of exciting developments here, both in architecture design as well as reducing supervision and the ability to have zero-shot generalization. So yeah, I showed you like a very quick, overview on some of what I believe are the exciting developments we've been seeing, both in the scientific realm, but also right in computer vision, trustworthy AI. And I believe all these we can distill it into like thinking about building new foundation for AI algorithms. Because, what we've seen is earlier we were focusing on supervised learning, but a lot of now new aspect is either doing unsupervised learning or semi-supervised, or thinking about distributional shifts, right? Your training data is different from your applications. And same with like the use of priors, right? Earlier we had weak or no priors, but in so many applications that I showed you, we strongly incorporate the priors. In the drug discovery realm, I'll give an overview later on how we incorporate domain-specific features like orbitals, right, which is very important to understand the quantum level properties, or in the robotic applications, right? We did model-based reinforcement learning on the robotic arm, but then we also kept the model flexible and open to adaptation. So I think this aspect is important, that now for robustness, we need better inductive priors, better domain knowledge. And lastly, the aspect of the task itself in so many of these applications could now be adaptive rather than static, right? So we saw in the robot applications, even though it was trained for just doing one kind of task, you can quickly adapt and transfer to new tasks. Same thing we'll see in the scientific simulations, right? So learning, say, and what I will see as an underlying operator for the family of partial differential equations will allow it to easily generalize and transfer to the problem instances or related physics. So I think these aspects are also, I think, important to all consider together. So I'll quickly take questions here before I dive into the topic I want to cover, which is the aspect of how do we solve partial differential equations. That'll be the main topic of the talk. And then, I can dive a bit into some of the others. But here, at this point, I also want to see if there are questions.
Is there any quick clarifying question from the audience?
I have a question for Anima. Perhaps you may talk about it later, I guess, about the PDEs that you said that we can generalize on different problems or from one PDE to the other. I presume you'll talk more about it, or should I ask you a question? Okay, I'll wait then.
Deep dive. This was the overview. So
okay,
although I took like half the talk with the overview, but I hope also wanted to kind of give an umbrella of different developments that I think are very exciting. Great. And so before we dive into that, another aspect that I so far didn't cover, right? I focused on algorithmic development, right? The other aspect is the hardware itself. I mean, I think so many people miss the point that deep learning would not be possible if not for GPUs, right? The parallelism at scale is so important to realize these models. And so where do we go from here? And so one aspect we've looked into is, kind of how do we design good quantization schemes that can have reduced energy, not just for inference, but also for training. And can you directly train in low bits, right? Like a small number of bits. And so this we show is possible if you did it in the logarithmic system, right? So kind of the high level takeaway is that it's better to put the bits in having a large dynamic range rather than having a lot of precision in the mantissa. And but we need new training methods to handle this, and the co-design really pays off. And then the other aspect of hardware design is also understanding how, for instance, we want to look at next generation hardware like quantum, right? So there is indeed a lot of excitement, but also a lot of challenges. So building efficient tools to simulate them on GPUs is really important. And also looking at algorithms which could give us quantum advantage, right? How do we do encoding better? I think is also useful. Sorry, I don't know if someone is not muted. There is. Yeah, there was a noise I was hearing, but I guess now it's gone. Thanks. Yeah, so I think this aspect is also important to look into, and I'll quickly give in the end some I think, results on this. But let me first dive into learning partial differential equations, which I really think of it as learning in infinite dimensions, right? Because what we have are systems that are really from continuous inputs to continuous outputs, right? As opposed to standard machine learning, which thinks of finite dimensional inputs mapping to finite dimensional outputs. And that's what makes these PDEs, one aspect of it, challenging, right? Because you have highly multi-scale phenomena, right? So depending on the discretization, you see different phenomena, right? So, and that's where for many of these, like say turbulent fluid flows or other complex systems, you're forced to discretize to the finest level in numerical methods, because otherwise you cannot accurately solve the problem. Right? And that's what makes them slow, because you have to do this fine discretization and you have to then kind of sequentially go through that, right, over time to predict the evolution. But on the other hand, the question is if machine learning can overcome these challenges by learning the underlying representation, so you don't have to go through this fine discretization. And that's really like kind of our, the way we think about this problem is, if you want just to solve one instance of PDE, right, there you're just looking at approximating solutions at all the query points, right? So it's just one instance. And you're not kind of worrying about the general properties of the family. On the other hand, if we want to learn a solution operator, we want to be able to predict for any given initial or boundary conditions, right, this corresponding solution, and on any query point or any part of the domain, right? So, and this is much more challenging because we want to now have a solver that can do this for any given condition. And so this is only possible if we can learn over a set of conditions, right? So initially we'll treat it as a supervised learning problem where we assume that there is a ground truth solver that can give us the solutions, right?
Please
that
press 1 from your dial test to enjoy system services.
Not sure what's going on. Yeah, so we have that, as the problem setup. As I mentioned, why this is just not a trivial supervised learning problem is the aspect that we have to do this learning in infinite dimensions, right? So instead of assuming a fixed grid or fixed resolution, we want to be able to directly learn the solution at any resolution, right? So at test time, we may ask the solution at a different set of grid points or a different resolution, and we should still be able to answer that. And this is the aspect of zero-shot generalization as well that's important. And so this is really the contrast, right? Like if you look at convolutional neural nets or transformers, they assume a fixed sized inputs, right, in a fixed resolution. Whereas we want to be learning systems, that map between function spaces, and those are in infinite dimensions. And so that's where we call this new framework we are developing that can learn such mappings as neural operators. Any questions here? Right now, all I've done is set up the problem and say, we want to go beyond the standard neural networks and formulate a system that can learn mappings in infinite dimensions. So then the next question is, how do we go about doing this? So this is where let's kind of go to a standard neural network, right? So, if you look at MLP or convolutional network, any of the standard networks, the basic premise is that, you have like your input, right? Typically you do some linear functions such as matrix multiplication or convolution. And on top of it, you add some nonlinearity like rectified linear unit, and you get the outputs, right? You can do many layers of that. So it's essentially composing linear operations with nonlinear operations to get an expressive universal approximator in finite dimensions. So we can take the same philosophy and now extend it to infinite dimensions, right? So now we can say that we can have layers that do solve for a linear operator, right? So you're learning a linear operator, and on top of it, you could do a standard nonlinearity like the ReLUs. And if you compose them, we can expect this to be a universal approximator for any operator. And the choice of what would be a form of the linear operator is where now the details, right? And here the intuition is that we want this to be an integral operator, because in the special case, if you just removed all the nonlinearity and you only did the linear operator, this should be able to solve linear partial differential equations, right? And we know the solution of linear partial differential equations are in the form of this integral operator. Here, this k would be the Green's function, right? And so we are convolving with the Green's function, and that's how we get the solution. So this is something, if you've taken any partial differential equation class, right, you would be learning this, right? So like, for instance, the heat diffusion equation, right? So there we know analytically the form of the Green's function, right? That looks like this here in the figure. And we know its convolution with this Green's function. So given this is natural to use that as a layer, right? So we have a layer that learns a linear operator, but then we compose it with nonlinearity. So this way we are not just limiting to solving linear partial differential equations, but now we have an expressive model that can even solve nonlinear PDEs. Any questions here?
Anima, I have a question. How would you represent an integral operator of the kernel?
Yeah, that's the next slide. So exactly. Okay. That's the next slide, right? I mean, this is kind of saying, as a principle, this should like now be able to approximate, right, any function. Now the details are in terms of what is the specific architecture to do this integral operator.
Okay.
Yeah.
Thanks.
And that's where, we again went back to what people are doing classically, right? And in so many scenarios, there's like good choice of basis functions, and a common one is Fourier transform, especially in like fluid flows. This is popularly used. And so what we can do is, instead of solving the convolution in directly in the spatial domain, we can do instead right, multiplication in the Fourier domain, right? So this is the signal processing 101, if you recall. Convolution becomes multiplication, right, in the other domain, in the Fourier domain. And so that's one of the motivations to use Fourier transform is it's fast, it's cheap, and we can learn the weights in the Fourier domain effectively. And the other aspect is, compared to standard convolutional filters, which are small, and hence the effective receptive field is small, these Fourier filters are global, right? And so they can capture global long-range correlations very effectively. And this is again important in applications like fluid flows, right? There is local phenomena, but there's also lots of long-range correlations. So if you try to do convolutional neural networks, you wouldn't be very successful with that. And so that's the other benefit of using these Fourier transforms. And so that's the framework. Now, what we are saying is we can solve the integral operator by learning weights in the Fourier domain. And these mixing weights among different frequencies, what we also do is to look at only low frequencies, right? We do filtering, so we are only looking at low frequencies and doing inverse Fourier transform. So we are kind of, right, effectively solving an approximation of the integral operator. But this regularization of picking only low frequency modes is not so problematic because we're composing it with nonlinearity, right? So it still keeps the expressive power. And of course, it's a hyperparameter to tune of in terms of how much regularization you want. But this regularization in practice, we've found it very effective for stability and for good training. So that's a detail. And one more detail is, sometimes the Fourier transform right, has a hard time with capturing non-periodic information, right? Because it captures periodicity very well, but for non-periodicity, it would need a lot of high-frequency modes. So that's where we can also have an alternative skip connection to learn this. In some of the other works, like this carbon dioxide storage, we even made this into a unit, for instance, right? So you can kind of have other architectures that capture local spatial information effectively that may be missed by this. So there's a lot of room for doing architecture design here, depending on what's needed for the domain. But yeah, the outcome is the ability to be training on just low resolution data in this case, right? So just 64 by 64 spatial, and directly evaluate it on high resolution, right? So this is the zero shot aspect that I mentioned. By using this framework, you can directly run this in any resolution and also get fairly accurate results. And I think that comes from this careful thinking about designing a system that is, having the foundation of operator learning. And we also see that in the frequency spectrum, right? So the ability to extrapolate to now higher wave numbers, because in low resolution data, you wouldn't have seen these, right, wave numbers, because it's not the resolution is limited in your training data. But still, you can now extrapolate to higher wave numbers, which is evidence that it's learning, right, the underlying operator better than UNet or some of the other frameworks. So these are some applications that I already showcased, but also there are many others. We've used this as initial experiments to look at, can we replace methods for predicting molecular dynamics, right? These time-dependent conformal changes in how the COVID-19 virus replicates, can we predict those movements fast and effectively? We've also looked at others like beamforming in ultrasound, looking at stress prediction in materials. And in this case, this was a multi-scale system where the core scale is still the traditional method. We only replaced the fine scale and got such a big speed up, right? So in some complex systems, again, going to the earlier point, we may not replace everything with machine learning, right? We may kind of augment the existing methods and other applications like computational lithography and so on. Yeah, so any questions here before I kind of talk about a further extension of this, where so far we didn't use any of the physics at all, right? We just said if you have ground truth solutions from an existing simulator, but we don't want to overfit to a single resolution, how do we generalize? But the next aspect, I'll also talk about how to incorporate the equations themselves into the learning. Petro?
Yeah, I had a question. What is the Reynolds number of the flow that you have simulated?
So in this example, if I recall the details are in the paper, so I don't want to say a wrong number. In some of the others, we've done it up to like 500, but this specific one, I don't recall because it's an older.
Yeah, no, so 500 is not the turbulent flow, as I understand. So one of my questions is it possible to train at a lower Reynolds number and then to extrapolate at a higher Reynolds number where a PDE will have actually problems solving it?
Right. And that's where we've seen in the next part, right, where we also incorporate the PDE laws, like incorporate the equations themselves. There is much more promise there to do that. We have gone from like Reynolds number 100 and transfer it to Reynolds number 500 and be able to then fine tune and get a much better optimization landscape. But yeah, indeed, into a very high Reynolds numbers and challenging cases, I think it's still an open question, although the weather simulations that we did, right? I mean, they're not numerical simulations, but like the hurricanes and those are high wind speeds and are turbulent. So, and there we've seen promising results. So, you know, I'm curious to kind of see how much we can push here.
Okay, thank you.
Great. Yeah. So to quickly, you know, like kind of cover this next aspect of how we can also make this physics informed, right? So using like the equation laws in addition to the training data we have potentially from the solver. And the idea is if you had no training data, right, you could still use the equation losses to train this, and that's what the physics-informed neural network does. But in this operator learning framework, what we are saying is instead of training on one instance, you train on lots of instances, right? And so that kind of like gets you a much better understanding of the overall optimization landscape rather than trying to solve one instance and you could get stuck. And the other aspect is, you know, if you want to further do test time optimizations or fine tuning, so you're not happy with what the accuracy is on a given problem instance, you can further use the loss of what the equation should be, right? Like the partial differential equations themselves, and fine tune that. And we've seen this way we can further reduce the error. Because unlike other cases here, we can easily verify if the solution is true or not, right? If it's the correct solution or not. And hence, we can further enhance the generalization ability of the pre-trained model. And so we see that, right, like this aspect of in this paper, we have results of being able to generalize from one Reynolds number to another. And also like seeing how much training data we need, right? So what we see is, you know, in PIN, you're just solving one instance at a time, right? And that is really bad for convergence. On the other hand, in our methods, right? So if you had like, say, you know, 400 samples from the simulator from a ground truth, right? And then the rest of it is just augmenting the equations, right? So for this, you don't need any supervision. It's just looking at just the equation structure without the solutions. So if you did that, right, then you get really good convergence. And so what this is saying is, of course, it's expensive to get training data from expensive simulators. So what you can do is augment it with a lot of examples of just the equations themselves without solutions. And you can learn a good operator ansatz. And so that's, again, I think, promising in data limited scenarios. And also the other aspect is solving inverse problems, which is a big aspect of requirements in many domains. What we've seen is the ability to, you know, directly learn the inverse operator or the backward operator, right? So from the solution, let's say, to the coefficients. And so you don't, you know, in the standard method, what you do is you have a forward simulator, and then on top of it, you do MCMC, and this is very slow because you're kind of first doing the forward model and then doing MCMC. But in this case, what we see is the ability to directly learn the inverse mapping. And this could be very effective in solving many inverse problems. So we've also looked at, chaotics, to Petro's point earlier, like, you know, which systems are turbulent or not. I mean, if you only did a small time frame, right, you can hope to predict. But if it's long enough, these systems are chaotic, right? So you cannot hope to exactly predict the trajectory because we know small errors will accumulate and lead to great divergence. And so the question is, instead of trying to exactly predict the trajectory, which is impossible, can we learn the invariant statistics of the system? And so with this perspective, what we did was to learn just the local evolution operator, right? So for a small time period, if you learn the operator, and then at test time, you can directly compose it, right? And this way, of course, you may not exactly predict the trajectory, but we can get the long-term evolution statistics of the model, right? So essentially the attractors and all the statistics. And so we see that here with different, you can look at like energy, you can look at density, different kinds of properties, and our framework learns it better compared to others. And also we can, capture this kind of global attractor here. Yeah, so any questions here?
May I ask one more question?
Go ahead.
So if you have one thing that has puzzled me with these approximations, if I have a linear equation and I solve it with the classical methods, I know that I maintain the linearity of the equation in the solution space. If we approximate them with nonlinear operators, how do you guarantee that you maintain linearity?
You don't, right? So it's a nonlinear approximator, and indeed for linear equations, maybe this is not the best one, right? The classical methods themselves are pretty fast, and we can look towards parallelizing them, which in many cases they are. So this is really meant for highly nonlinear and complex systems, right? That would be very slow with classical methods.
Okay, thank you.
Anima, can you say something more about the inverse problem, about the inverse operator from the solution?
Yeah, I can dive into that a bit more here. So, so the idea is, right, so these are the initial coefficients, right, and the U is the solution. And so there are two approaches, right? You can first learn the forward operator, and then try to infer what is a good fit, right, for this A, right? So given U, what is the A? So whereas on the other hand, you could also directly learn the inverse mapping or the backward operator, right? So you're now solving for directly, right, recovering U, right? So from this mapping. And so you can train the operator to solve for the inverse problem directly.
And how would you, what kind of architecture do you use to represent this backward operator?
Similar, like the Fourier aspect. So we did, I think, we may have tuned the hyperparameters of layers and the details, but similar architecture. Because, ultimately, whether it's like the forward or the backward mapping, right? Both of that we can express in this framework, right? Because this is a general expressive model. But I think the main kind of aspect is if you're trying to learn the inverse mapping, you can train to learn it directly rather than first train the forward model and try to then do MCMC, because that would still be slow.
Understand. Thanks.
Great. I know I have just a few more minutes, so I can't expect to go through everything, but just one point I want to cover is there's actually some nice connections between transformers and these neural operators, right? In what you can think of what's happening in a self-attention layer in the transformer, right? Essentially this attention mechanism, if you looked at the continuous extension of it, it's an integration, right? So that multiplication, in general, you can think of it as integration and mixing of tokens. So, and if we view it under this lens, what we can do is replace the self-attention mechanism using our Fourier neural operator. And essentially the idea is we can do this spatial mixing through now a layer of Fourier neural operator. And then we can also learn how to mix different channels within the layers of transformers. And so with this aspect, what we get are the benefits of using Fourier transform, right? So it's much faster than self-attention, which is all-to-all and quadratic in cost and very expensive and limiting for doing high-resolution models. And the other aspect is, being we did further like architecture design to make these neural operators efficient in the setting of transformers like weight sharing. I won't get into that here, but the main idea is you can be now having the same quality as the full self-attention, but having much fewer number of flops. So you're getting efficiency by using these frameworks. And not just that, these models also seem to learn good representation in the intermediate layers, right? So this is the full self-attention. This is our neural operator-based self-attention. And even though there are other models that also are efficient, they don't seem to learn good intermediate representations as well as our model does. So again, kind of right, there are interesting connections in terms of how we think about spatial mixing when we do vision transformers, and these models have an interesting way to speed up those operations as well. Yeah, and in terms of like making all this work at scale, we are building that into an NVIDIA platform called Modulus, where we will have these neural operators, physics-informed neural networks, all this be parallelized, right? And forward, inverse, and data assimilation problems. So really like making it easy for people to have pre-trained models as well as tools to easily start working in these areas. Yeah, thank you. I'm happy to take questions.
All right. First of all, thank you very much, Anima, for a very interesting overview talk. I see that we have accumulated a few questions in the chat box. One of the questions is, can you please elaborate on how you use FNO for the molecular dynamics cases?
Yeah, the main idea there is, right, we know like there are forces on atoms, right? And with the conformal changes, essentially there are equations of motion, right? That, but of course, the complexity is how they all interact at scale. So what we did was to use the trajectories from the traditional simulator, and then we used our neural operator, but in this case, we used a graph-based version because, right, of the graph structure we have in molecules. And then we were able to show that it can capture the trajectory pretty well.
Thank you. I saw Jimin had a question. Jimin, please, go ahead. I don't know, probably Jimin cannot unmute himself. So for now, let me switch to the question in the chat box. So the question is, if you can comment on the difference between neural ODE, which approximates ODE function with a neural network in a continuous space, and the Fourier neural operator that you mentioned in your talk.
So the neural ODE still uses ODE solver, right? A traditional ODE solver, whereas we are learning to solve both ODEs and PDEs.
Okay, Jimin.
Thank you. Thanks for a great talk. I just want to go back to the Hurricane-Matthew case. When I watched the short video, it seems like the trajectories are on top of each other. Is that correct?
Which trajectory? I mean, that's just the contour map of the different wind speeds.
No, the simulation track seems to be on top of the actual track. Is that correct? Or
yeah. So it's like there's contours around, right? And then from that we can simulate.
So the contour, I thought the contour was the NOAA prediction. It's not.
No, the white is the NOAA prediction. The purple was our prediction. Let me go back to that.
Thank you.
It's all the way back. Yeah, so the purple one is our prediction, right? So like the contour maps. And the red is the actual trajectory. And the white is the NOAA prediction.
Okay. All right, thank you.
Yeah.
And is this typical behavior that you saw in other, is it typical behavior that you saw in other cases as well?
In the sense of the
better scale.
Yes, the spatial resolution is where we are able to do much better, right, compared to other methods. I mean, same with like even the Navier-Stokes examples, right? The ability to solve the higher resolution without even training on them, right? So that shows the aspect to capture more fine scale features.
I saw a question from Sergey, please.
Yeah, thanks. So we have external world which we are observing, and we have differential equations which we use to describe it. So now question is if you're trying to understand the world better, you're trying to find contradictions in between systems of equations that you're using and real world. So now, and you're trying to direct your experiments towards places where you see these contradictions. So like in this method, can you do same? Like, will be it helping us to find these contradictions, or it will be masking them?
Yeah, that's a good question, because in the first part we didn't use the equations at all, or any model assumption. We were directly learning from data. So one thing what you could do is you could just directly learn from data. You could learn only based on equations, right? And then look at the disagreement between those models, right? And that would, potentially give you the ways to choose cases where there is disagreement with the model. If that answers your question.
Okay. I have one quick question, Anima. I remember in early parts of your talk, you briefly mentioned the training, directly training neural networks on quantized, energy-efficient hardware. Can you make a brief comment on that?
Yeah. So the main idea is to do it in a logarithmic scale, right? So instead of uniform quantization, which is what people usually do, this is highly non-uniform because as you increase the magnitude, right, you have larger quantization gaps. And so for this, we did multiplicative updates instead of additive updates like stochastic gradient descent, right? Because in multiplicative way, you're also now taking bigger jumps as you go to larger magnitudes. And so that combination is what made it possible for us to keep everything in the logarithmic format, right? And the multiplication is, going to save energy because it's just addition. But if you want to do addition, right, then we kind of did like a Mitchell's approximation. So this is the classical one, like a table lookup with a reduced table lookup. And the thing is, if you train with that, you also learn these approximations. And so that's what gave us this end-to-end benefit.
I see. Thank you. I saw a question from Wenjing. Please go ahead and mute yourself.
Okay. Hi. I just have a quick question about the part where you do quantum mechanics for protein understanding, because we're trying to do something very similar to that, deriving the electron structure of the proteins through the quantum mechanics. Could you direct me to what papers is the best publication to read about it?
Yeah, so OrbNet is the name. So if you look up OrbNet,
Okay.
the the first starting paper, and then I can also share these slides, so that would have some of the details. And from ArbNet, we then had a version that incorporated symmetries. We called it Unite. So those are the, but yeah, if you Google ArbNet, I think that's the starting point. And the main idea is we're kind of combining the orbital features with graph neural networks. And in the later, we also make it equivariant. So the symmetries are, handled.
Okay, great, thank you.
So a follow-up question regarding the quantization in the logarithmic domain. So Jacob had this question, wouldn't updating in the log space cause numerical stability issue, because small errors are now in exponents rather than in the standard domain?
Well, that's what we're learning in that domain.
Right? The number you have dialed is not assigned. Aradığınız numara kullanılmamaktadır. The number you have dialed is not assigned. Aradığınız numara kullanılmamaktadır. The number you have dialed. Aradığınız.
Apologies for that. We'll have to find out. I think sometimes we get bombed, Zoom bombed here, Anima. Apologies for that.
No worries. Yeah, so, because we are training in that domain, right, we don't see these instabilities, right? We are also like kind of, having a large dynamic range. And yeah, so it's, I guess maybe a bit surprising, because we don't even keep high precision copies during weight update. We directly, update it in low precision.
Great. Any other question from the audience? And Andreas, please.
Yes, first of all, thank you very much for the good presentation. I have a quick question. You showed mainly for the fluid dynamics cases, 2D cases. Is this method also applicable to 3D?
Yeah, we're now doing that underway, and a lot of it is the scale, right? Like kind of to have now much larger models and even look into model parallelism, which makes it more challenging.
It's what path are you following on this model parallelism and or data parallelism?
Yeah, so we're looking into these more, one is right, these transformer models on the channel domain. It's easier to parallelize. So that's one route we are taking, but we are also looking into multi-GPU FFT itself, like QFFT. If we can, get good performance, then we can distribute it. But yeah, this is still very much an open question.
Okay, so the things that you've shown basically ran on one GPU.
I mean, data parallel we've done in some scenarios, but not model parallel.
Okay.
I mean, the weather model was like 128 GPUs or so.
Okay, thanks.
Okay. If there is no more question, let's thank our speaker, Anima, again.
Thank you. Thank you. It was a pleasure. And yeah, reach out to me if you have further questions or any pointers, references you want. Thank you. Thanks, everyone. Thanks, Petros. Bye.